Okay, welcome back everyone to today's talk in the College Seminar on Differential Algebra. Today we are very happy to have Kilian Raschel, who will give a presentation on singular walks, Bernoulli numbers, and differential transcendences.
Thank you. So thank you very much for the invitation. It's a pleasure and an honor to be here. So I will speak about a joint work with Aline Bostan and Lucia Di Vizio. So we are all working in France. And so I will speak about some combinatorial model in the first two parts. So we'll speak a bit about random walks and combinatorial walks. And in section 3 and 4, I will try to give some ideas about the proofs and in particular to give a kind of a probabilistic approach to interpret the transcendence results that we have proved. But first, we need to make some effort in combinatorics to understand which kind of models we are studying. So let's go. So we'll speak about walks in certain domains, and maybe to explain the simplest possible model, I should speak about dimension 1. So maybe you can take a look at these two pictures here. So we have walks in Z. So on this horizontal axis, we have the time. And we have walks which move either up or down. So it's a very simple model. It's called the simple random walk or the simple walk. And so I have made two different pictures. The one on the top can move anywhere, I mean, positive and negative values. And if you look at the one here, every time you are on the horizontal axis, you cannot go down. And in a way, we force the random walk to stay non-negative. So it's two different models. And of course, it's a bit more complicated to understand the second one because we have a constraint on the path. And it's very classical in probability and also in combinatorics to study these models. There is a long tradition, in particular to give, in this case, explicit expressions for the number of walks. So to understand a bit what kind of quantity we are going to look at, maybe you can take a look here. So we will look at trajectories between the point 0, let's say the origin of the plane, and any point which I'll call I here. And I have walks of length n. And so I have two variables, I and n, and I want to compute this kind of combinatorial numbers. And in this talk, I will look at many generating functions. So instead to look at these numbers of paths, I will look at the generating functions where I take the sum over all possible I and n. And so I need to add the two variables x and t. Okay, so the goal is to find formulas, for example, for this kind of generating functions. So this was for dimension 1. And so in dimension 2, it becomes even more complicated and interesting. So maybe you can look at this picture here. So I took a pair of two one-dimensional random walks. And imagine that I look at the distance between the two paths here, and also the distance between the bottom one and the horizontal axis. Then I get, in a natural way, a walk in a quarter plane, because I have two positivity constraints. So the main object in my talk will be this one here. So we have a random walks in dimension 2, and we have this a quadrant or quarter plane condition. And we would like to enumerate the number of walks which move in this domain and stay in the domain. So in the same way, we can introduce some generating functions. So now it's called a Q because it's for a quarter plane. And we look at the path between 0, 0, the origin, and any point which I call I and j of length n. And now, so it's a trivariate generating function. I have three variables, two for the space and one for the time. And again, so I want to give some formulas or to say something about this kind of functions. So I have no time to explain, but in the slide, you can see many motivations to study this kind of problems. And in particular, I am a probabilist. And in probability, we are now interested in random walks in cones. I mean, in any kind of dimension, not only 2 or 1, any dimension. And there is a huge activity on this right now. So it's just one example. If you take the quarter plane, it's one of the simplest possible examples. Okay, so I mean, I don't want just to speak about combinatorics because I know it's not a combinatorial seminar. So I want to make the link with some equations and differential equations and so on. And to that aim, I need to introduce some quantity which will be called the kernel. But first, so we fix a model in the quarter plane. I will call it S, and it will be a subset of these 8 neighbors. So for me, a model will be the data of a kind of choice of a model, and I can take any subset of these neighbors, and it defines the moves, the possible moves for the random walk. So we have, of course, many choices for that. And once you have fixed one example, then we define a nice and very important polynomial, which I call k here. So it's very easily constructed. Maybe you should look at this red part here. Every time you have a jump in the step set S, you should add some monomial in this quantity here. So for example, if you have the move right, so the arrow 1, 0, then we will get x at the power 1 and y at the power 0, so just x. And every time you have a jump, you have a term here. So it's a biquadratic polynomial in x and in y, just because we have a small steps. And you see we multiply by x and y here. So even if you have a term like 1 over x, 1 over y, because of these terms, we are going to have some polynomial. So it's a simple biquadratic polynomial. And the key point is that we have a nice functional equation, which involves the kernel k and the series, which I introduced a bit earlier, q. And so maybe you have already seen it. So it reads, so k times q, so it's a product of generating functions or polynomials for k. And on the right-hand side, we get a sum of different terms. And each of them, in fact, is exactly the same as on the left, but we evaluate at a different point. So for example, that's x 0 here, y 0, etc. And we have some non-homogeneous term, x times y. So if you see this equation for the first time, maybe it's a bit surprising. It's one equation and we have one unknown. So maybe you could think, okay, we are going to solve it in 1 minute. So it's not so simple because, of course, we have trivariate or bivariate generating functions. We need to find some ideas. So this is the key starting point of the talk, and which is the relation between this combinatorial model and difference equations or differential equations. So before continuing, I wanted to take two examples to show a bit the type of formulas that we can hope for. So if you take the simple random walk, which is by definition this one here, it's if you can move just to 4 neighbors. Okay. So I will not explain why, but the point is that we have a very nice and simple formula for the number of excursions. I mean walks between 0, 0, the origin, and you go back to the origin in 2n steps. And for some reason, there is a nice expression using these Catalan numbers, which is one of the most famous families of numbers in combinatorics. And we also have a formula for the series, so q of x, y, t. And I wanted to spend maybe 1 minute on this formula because I think it's important. So here we have a rational function. And maybe you have recognized that in the denominator, this part here is exactly the kernel. Or maybe more, all the denominator is equal to the kernel. And we have a simple polynomial in the numerator. And so the point which is not totally classical is that, so this is a Laurent series in x and y. And here we have this operation that we take just the positive terms, concerning the valuation of x and y. So we have a kind of complicated series and we extract just a part of it using positive valuations in x and y. And so it's a nice expression, which is quite easy, in fact, to obtain. And what is even nicer is that we can prove from it that we have a differentially finite function, a function which satisfies some linear differential equation. So a simple example, we can explicitly compute the series and even say that we have some linear differential equation. So it's a nice model because we can really solve it. And in some other examples, so I will not spend too much time on it. If you take now this one here, another simple 3-step model, then we even have an algebraic, if you look here, algebraic generating function. So we have many examples, and if you give me one example, maybe I can compute some terms or say something more. So now this is kind of a classical slide for people like me in order to explain a bit what we want to do. So we have many possible models of walks in the quarter plane, and we want to classify the series according to the type of differential nature that it has. And so you all know, I guess, this hierarchy of functions. So we have rational functions. Then we have a slightly bigger class of functions called the algebraic functions. And we have these definite functions, which, so by definition, satisfy linear differential equations. We have an even bigger one called de-algebraic ones. So you can take a look here. It's when we have a differential equation which could be algebraic. I mean, some have some product terms also. And then we have the rest of the world, which is composed by differentially transcendental functions. So by definition, if they do not satisfy any differential algebraic equations. So of course, if you take a random function, it will be differentially transcendental. Yeah, it's the norm, let's say. Anyway, so we have the combinatorial problem, and we want to understand more where we can put our series. And so, of course, when speaking about differentially transcendental functions, we should mention the gamma function. And there is this nice theorem by Hölder, which says that gamma, of course, is differentially transcendental over the field of rational functions. And the link with the rest of my talk will be that the d gamma function, I mean the logarithmic derivative of the gamma function, satisfies a very simple difference equation that you can read here, which is of course related to the classical functional equation for the gamma function. And there is a link between such difference equations and the differential nature of the function. So I'm going to show this later. Okay, so now this was a kind of interlude to speak about the nature of functions, and I go back to the classification of my quarter plane models. So yeah, I wanted to speak about this result because I think it's interesting. Remember, so we had this kernel which was associated to the model S, and here I'm just looking at the zero set of the kernel. So we have a model, we have the kernel, and we look at all the points in C2, I mean in the complex plane at the power 2, which are such that the kernel is equal to 0. So we can view it as a Riemann surface, of course, because we have two variables and we're in the complex plane. And if you know a bit the theory of Riemann surfaces, we can associate some transformations, some automorphisms called covering or deck automorphisms. So they are quite naturally associated to this polynomial. And so now we have a group transformation. So I have no time to properly introduce it, but let's say we can canonically associate a group. And the point is that so this group should be either finite or infinite. And so I give two examples here. On the green one defines a finite group for some reason, and the red one appears to be infinite. And the very nice result that so people have proved is that Q appears to be definite if and only if this group is finite. So it's a nice geometric interpretation of the series being definite or not. And what is also nice is that it's not just one result, it's really a combination of a lot of works by many people. So I didn't want to take any risk by quoting anyone in particular, which proved this result. So what I wanted to say is that somehow, you know, in this hierarchy of functions, we know where to put the functions because we just have to compute this group. And according to the finiteness, we know that the function will be definite or not. So of course, if we have a definite functions or even a differentially algebraic, so people in combinatorics are happy in the sense that they can say a lot of things about the model. Maybe they can compute some expressions, I mean closed form expressions. They can deduce asymptotics So we all know that if we have a definite functions, for example, the asymptotics should be very specific. We cannot have any type of asymptotics. It's very constrained, etc. So if we have a definite model, we have constructive results. It's a positive result, and we can say more. We can compute or, I don't know, study more the models. And so it's a bit the question which I am asking in my talk. What happens if we have a model which is differentially transcendental? In fact, it can happen. So a priori, we can say, okay, it's a negative result. So we know that we're not so happy. We just say we have a complicated model and we don't know what to do with it. But if you look a bit more closely, in some cases, we even have explicit expressions for this model, so kind of constructive results. We can still use probability theory and approximate by a Brownian motion to have asymptotics. So we have a lot of positive results. So we wanted to understand a bit more what we can say about this a priori complicated models. And on the right, I have put two examples of models. And so I can say to you that one of them is differentially algebraic and the other one is differentially transcendental. But it's very hard to guess who is who because I mean, they are just related by by a simple transformation. Just you have to reverse one jump. So it's surprising, and we wanted to understand this. And so even if it's maybe a bit ambitious to state it in this way, we wanted to provide a probabilistic interpretation of transcendence. Okay, so sorry, maybe it was a bit long as an introduction, but I think it was important to take some time to properly introduce the combinatorial model. And now I will be more specific, and I will look at this subclass of singular walks, which will be, in fact, the topic of my talk. So what is a singular model? In fact, it will be one of these five examples, which I call ABCD. And in fact, I will just, most of the time, I will speak about the first one, A, but all the result applies somehow to all the family. So it has been a family of models introduced by Marni Mishta and collaborators back in 2007. And so they have a nice structure. In fact, maybe we should start by this picture on the right here. Imagine we look at the model A here, which starts at the origin. So we have this very nice recursive construction. At the first time, we are going to use the step 1, 1, because we want to stay in this quarter plane. And then we can fluctuate on this small diagonal segment up to some time. And again, we continue. So at some point, we're going to use a 1, 1 jump. And we are back to a new segment, etc. So it's a very simple recursive construction. And we understand that there is a connection between this model, of course, and walks on segments. And in combinatorics, I mean, everyone knows about walks on segments. It's a very classical model because it's a finite graph, and it's the simplest situation, I would say. And on the left, I have represented one possible path of the model. So you see that we go in this direction 1, 1, and along the way, we fluctuate as it's possible to do. And so I think it was named singular because if you think of the kernel, it corresponds to kernel of genus 0. So I said that the kernel defines a Riemann surface, and a priori it can be a genus 1, genus 0, and so on. And in these cases, exactly correspond to the one which have a genus 0. So it's a particular case which is, let's say, consistent. So in fact, in the literature, there is some earlier study about this model in the probabilistic literature. It was more about this blue family, which is not the red one, I mean, directed to infinity. The blue one is more directed to the vertex of the cone because, people at the time were interested to different quantities. But anyway, so they started to study this class of model. And in the paper of Marni Mishta and collaborators, they proved that we can obtain a series expansion of this model. So they computed the generating function first. And what is very interesting to us is that they proved that the series was non-definite. And the argument was very nice. I mean, it was related to this recursive construction. In a way, we could say that each segment can generate some poles. And in the end, we're going to form an infinite family of poles. And we know that it's not possible for a definite function to have an infinite family of poles. So it's really due to this recursive structure. And more recently, there has been a nice study so by Thomas Dreyfus, Charlotte Ardouin, Julien Roch, and Michael Singer, who proved that in fact it's not only definite, non-definite, but even differentially transcendental. So it's really a complicated series in that sense. And of course, this group of people also studied the Genius 1 case, but I will not speak about this later. But it was very nice to have these people involved because it created a kind of nice collaboration and input of Galois theory into this topic. Okay, so now I wanted to state the results of this paper with Aline and Lucia. So the first one maybe could appear a bit naive. We wanted just to define the function in the biggest possible domain, which you could say, okay, maybe it's not important, but in fact, it will be important. So there is an easy upper bound, because if you have a walk and you have a step set S, a priori, at any time, you have a cardinal of S possibility to continue the walk, okay? The number of steps. In practice, we have a bit less because imagine we're on the boundary of the quarter plane. So we don't want to exit the domain by definition of my model. And so in this boundary points, we're going to have strictly less than cardinal of S possibilities. Okay, so we feel that maybe we can do better. And in fact, what we proved is that you can go from 1 divided by cardinal of S up to a half for any of these ABCDE singular model. So it's a kind of a universal, from that point of view, point where you can define the series. Okay, so we accept this for now. And now, because we have a series which is well defined, we can evaluate at a half. And what do we get? So we get a series in X and Y. And each term here is an infinite series because we sum over all n. And then we have a strong sign that something is happening because we prove that all coefficients turn out to be rational numbers. So it's very in Q and not in R, let's say, as expected. So maybe we will understand this later. Okay, so first part of the results, we can extend the series, and at t equal a half, we feel that something a bit weird, I mean a bit special is happening. So now we speak about the differential nature of the series. So I have mentioned the result that for any t between 0 and a half, we know from the work of Michael and collaborators that Q is differentially transcendental. So we gave us a refinement of this, but the main result was already obtained in the work. And what we proved is that now if you evaluate at a half, we have a strong form of differential transcendence. And what do I mean by strongly transcendental? I mean that we have a transcendence over the field of germs of bivariate functions meromorphic at 0. So maybe just we can spend 1 minute on this. So think back about this gamma function of Euler. So the gamma function, we know that it's differentially transcendental. But of course, if you allow a meromorphic function, it will be just, I mean, it's already a meromorphic function. So the gamma function is not differentially transcendental in this sense. So what we proved is that we have really a strong differential transcendence because even the gamma function is not included in this definition. And so we have a kind of jump of a transcendence between the classical case, so t between 0 and a half, and this singular point, a half, where we observe a stronger version. And finally, so we also like, in combinatorics having explicit formulas. So we're able to prove nice, I mean, to see nice numbers. So imagine you put y to be 0, and we compute this series here. We're able to prove that we have a connection with Bernoulli, some Bernoulli numbers, which are very classical numbers, which are defined here. And so the link between this and different equations is that in fact there is a simple so-called a tau difference equation satisfied by the function q at t equal a half, which takes the form f of tau. So tau is this homography here, is equal to f, and then we add a small rational term. And so before speaking about the proofs, I wanted to conclude the results by mentioning this. So we just proved that the function q is in fact strongly transcendental. So I mean, it's really a complex, complicated function. But in fact, if you look at the coefficients, they satisfy an absolutely simple recurrence relation because, as you can see, an plus 1 is equal to a kind of sum of binomial coefficients and product of the a. So we wanted to understand the frontier between differential transcendence and differential algebraicity. As you can see, it's really tiny because if we replace the ordinary generating function by the exponential generating function, meaning that you put some factorial in the denominator here, then these numbers indeed become the series expansion of the tangent function, which have a very nice differential equation. So it's a bit the question, so what is the interpretation of being a hypertranscendental if you have such simple recurrence relations at the level of the coefficients? Okay, so now I will speak a bit about the proof. So let me start by the case at t between 0 and a half. And again, so let me recall that most of the proofs is contained in the paper which I mentioned before. It's more here to understand the global thing and the difference between this case and the critical case t equal a half. So the approach is quite classical. So we have this kernel here. I take the model A. And because we know that we have a Riemann surface of genus 0, there is a classical theorem saying that we can parameterize or uniformize with rational functions. So it's exactly what I do here. I say that the zeros of the kernel can be represented using these quite simple rational functions. Just note that we have replaced t, so the time t, by a small function of v to have something fully rational. And then if you use this together with the very first functional equation which I have shown, you get in a natural way a q difference equation for this function g. So what is g? It is a function q evaluated at this coordinate of the uniformization. And then we can prove a q difference equation for this function. So it's a simple one because it's a really a g of let's say qs minus g of s, and here we have a simple rational function. So how is it possible to conclude and to prove that we have a differential transcendence? We have so I guess you all know this result by Ishizaki or Ogawara, which exactly applies in this situation. So imagine we have a q difference equation where q is not a root of unity, and of course also not 0. And a and b are just rational functions. And we want to characterize f, which is unknown. So for us, it's even simpler because a is equal to 1. And we have this dichotomy result, which says that either you have a very simple function, I mean a rational function f, or the solution is differentially transcendental. So it exactly applies to this case. And by studying a bit the poles and how these poles propagate, we can prove that the series cannot be rational, and so it has to be differentially transcendental. And of course, so it's a nice result. We have a similar result for difference equations. And in a recent paper by other authors, there are even stronger results, for example, for tau equations or difference equations of a higher order. Okay, so now we move to this critical point at t equal a half. So it's really a degenerate case here, because if you look at the kernel, it will even factorize as a product of two degree 1 polynomials. So it's a very simple situation. And so the uniformization becomes obvious because you can just take, okay, y will be a solution, for example, to this nice monomial factor, and it gives one possible uniformization, let's say. And so in this case, instead of having a Q-difference equation, like here, we have a tau difference equation. And again, so tau is this homography which is fully characterized. So this is the main difference between the case at t equal a half and the other case. So now I wanted to spend some time about this tau equation because we see that it's a kind of important quantity, I mean, important equation for us. And then we found this nice result by Martin Klazar in 2003. So Martin Klazar looked at this certain number of partitions, classical numbers in combinatorics, which have a very simple exponential generating function. You know, it's a kind of iterated exponential generating function. And he proved, in fact, two results. The first one was that this function, oh, sorry, I mean, not the exponential one. I mean, the classical generating function, the ordinary generating function, if we don't have this factorial n, satisfies exactly a tau difference equation, just based on combinatorial manipulations. And as a consequence, he was able to prove that the function b is in fact strongly differentially transcendental and strongly in the same sense as ours. So we have exactly similar results, I would say. And so just observe the connection with the gamma function of Euler, because if you look at the homogeneous equation associated to this equation here, a solution is given by the inverse of the gamma function. And so it was the starting point of an earlier work, which I will not have time to discuss today with Aline and Lucia. And we wanted to understand this tau equation and how it was possible to prove a differential transcendence in a broader context. And to explain a bit what we did, so we introduced one transform. I mean, we didn't introduce because it was known before, the Borel transform. To any ordinary generating function, you can associate the exponential generating function. And this function phi is this tau, the action of tau on a generating function. And there is this simple observation that there is a relation between having a tau equation at the level of the ordinary generating function and just multiplying by some exponential term at the level of this exponential generating function. So we can really play between a tau equation and just very simple differential equations with this prize to play between ordinary and exponential transforms. Anyway, so imagine you take the Bell numbers generating function, which is very simple if you look at the exponential one. We can immediately deduce a difference equation here, a differential equation, sorry. And using the correspondence, we can deduce a nice tau difference equation for B. So it's a kind, you know, of effective automatic way to think about these equations, which we try to systemize a bit. And in fact, we observe that in the literature, so sorry for this dense slide, we have many examples for which this is exactly the situation. So many families of polynomials that you have met probably have a simple exponential generating function. So this is this column here. And so if you apply the technique which I mentioned, you will get naturally a tau difference equation of order 1. And so you can prove that, so later we can prove that we will get this a strongly differential transcendence. So we can play between them. And so in a paper with Aline and Lucia, so this is the main result. If you have a tau difference equation of this kind, So again, we have A and B, which are rational functions, and we have this tau equation on W. We prove that we have a dichotomy result, exactly as Ishizaki. Either we have a rational function, or the function should be differentially transcendental in the strong sense. And so the proof is, this is a result in its own, I mean, which has a proof using a differential Galois theory. Okay, so I come to the last section of the talk. So now I will try to speak a bit about probability and to convey an idea to explain the difference between this t equal a half or t less than a half cases from a probabilistic point of view. So to do this, I need to introduce a tool in probability which is called the green function. So I don't know if you heard about it before. It's a very classical topic. So maybe you know about random walk. And a random walks, you know, one of the most classical questions is to say whether it is recurrent or transient. So what does it mean recurrent? It means that if you have a random walk, will it return or not with probability 1 to any point in the domain? So it's a classification of stochastic processes. And to answer this kind of questions, it's already based on this green function. So all the probabilists know about green functions because it's related to this classical classification of stochastic processes. Anyway, so this is the main relation here. Imagine you divide, in fact, the number of walks between 0, 0 and ij of length n by the total number of walks, I mean cardinal of S at the power n. Then naturally we get a probability just because we have normalized by the total number of possibilities. So this is a probability that a uniform random walk start at 0, 0 and end at the point ij after n steps. And once you have this definition, we can define the green function. By definition, it is a generating function. So over all this t to the n. And so we sum all the probabilities. So as you see, it's very related to the rest of the talk because we have generating functions and we have the number of walks. And among all values of t, there is one which is special. It's t equal 1. And why is it special? Just because, of course, if t is equal to 1, all this t vanish. And then we have an interpretation as an expected number of visits of the random walk at a point ij. So you have this random walk and you just observe along the trajectory how many times it will go through this point. So it's a nice interpretation. And what I will do now, I will interpret exactly our number of walks as green functions and to make the connection. So I see that, so maybe I will just use 1 minute and I will conclude. So this is a connection between the function q, I mean of my talk, and a green function. So we have a small normalization because if the green function is evaluated, if q is evaluated at t, because we pass from probability to combinatorics, we have to multiply by cardinal of S here. And all the question is to say, okay, this nice identity, is it possible to evaluate it at t equal a half or not? So how much can we do in that direction? And yeah, so I'm sorry to disappoint you because I have no time to explain exactly what this last idea. But the point is that exactly in probability, there is this nice transformation called a Kramer transformation, and which allows us to understand what it means exactly to change a bit the points of evaluation of the green function. So in one sentence, it's equivalent to change this point or to modify the weights, the probabilities of the random walk. And so the conclusion was that at this point, t equal a half, we can no longer perform this transformation. And so it's a kind of way to say that there is an obstruction at t equal a half because we can no longer interpret the numbers as a classical grid functions. And so this was the main difference between these two cases, t equal a half and t less than half. So yeah. So thank you very much for for listening to me.
Thank you very much, Kilian, for this very nice talk. Very interesting. We have a bit time for questions, so please just unmute yourself or write in the chat for questions for Kilian.
If I may ask you some question, perhaps not quite related to what you're talking. So all these results and techniques are for random walks when you're given some walking rules. Is that correct?
Yeah, it's correct. Yeah.
Yeah. So now suppose I want to say I like to check out how computer games are actually designed or constructed. So suppose I give you a bunch of points on the plane, which are nodes where, let's say, a player would visit. And let's say on every node, there is some treasures that you can pick up, the player can pick up. And then depending on that treasure, the way that the player would move depends on what he picks up. Now, in the design stage, now, of course, I mean, that can be random, I mean, the way they pick up the treasures and so on. But in the design stage of the game, I would like to say that at every point and every pickup of the treasure, I have some deterministic way of forcing some walk so that, let's say, they would get trapped in a particular node or something. Is there any technique to study those more deterministic cases?
So I'm not sure I fully understand the question, but I think it corresponds to what we call a non-homogeneous random walks, meaning that, instead of having the plane or the quarter plane, and you can move according to the same rules at any point, of course, we can modify by adding, for example, the rules that you have mentioned. And the rules can be dependent on the sides of the lattice, for example. And
Yeah.
so in general, I mean, it becomes much more complicated because for example, the functional equation is really based on having a homogeneity in the rules. But maybe, I mean, if you're able to provide some nice example where you have some rigidity or some consistency in the rules, maybe we can say something. But of course, it depends on the model. So we should speak more about which exact model you are referring to. But yeah, I'm sure it's interesting.
Okay. Yeah. I'm really just thinking in the design stage. I like to be able to control, how the walk would go, perhaps eventually, or just at some particular bounded time that I would allow the player to continue playing. So in those more deterministic way of walk, with some random component at the picking of let's say, the treasure. But for me, if I'm a designer, there's no randomness in the pick. I just have to really have some method or algorithm that once you pick a particular treasure at a particular node, I could force you to go certain way. So is there any study in those kind of not quite random walk, more deterministic walk?
Yeah. Yeah, I mean,
An example would be, let's say, I mean, very simple. Let's say I have a couple of nodes.
mhm,
Let's say on the XY plane,
mhm.
on every Y, let's say I have two nodes only, and then
Okay.
you can go from one node to the other as one of the walking rule. And let's say I can go up one level, all right, and then I can of course go backwards, depending on the situation. So is there any way to study those walks?
Yeah, I'm sure.
Not allowing everything is random. I mean, if you just say everything is random, then of course your things would apply, your results. But I'm thinking more
Yeah,
about deterministic.
I think that every time you will have some rules, and I mean, which is local, I mean, which just depend on the sites. We can at least try to formulate some equations and to have these recurrences, which is fundamental, I mean, in this domain. The thing is that you can construct a walk of a certain length using walks which are a bit smaller. And this is a way to generate recurrences. So, I mean, the only question is your model sufficiently simple to have a solution? But at least I think we can just write equations. This, I would think so, yeah.
Okay, thank you. Is there any way to I mean, basic books or reference to read about that?
Yeah, I can send you an email with some references. I would say that maybe a good reference would be to look at random walks on graphs.
Okay.
Because
Yeah.
typically people are exactly interested in this estimation of probabilities that a random walk will reach a point starting from another one. So yeah.
Okay, thank you.
Here's some questions by Bertrand Teguia in the chat, which I'm reading now. So it says, thanks very much for the great talk, Kilian. And if I see that correctly, that would be three questions. Let's see, the first one. I was wondering if you are aware of any models that are known or suspected to have d-algebraic generating series, but corresponding differential equations are not known. If so, please could you recommend some references?
Yeah, so it's a good question. So we have a paper with Olivier Bernardi and Mireille Bousquet-Melou. So in which we're able to prove that we have some exceptional models which are indeed differentially algebraic. And so in the paper of Michael Singer and collaborators, they also have these smaller families of models for which we have differential algebraicity. But at least in our paper, we are not able to obtain the differential equations. And I'm not sure that, so maybe if Michael is still here, he can tell us if they did it. But I would say it's all the examples are open questions, I mean, to find real differential equations. So the answer is yes. It's possible. All the models, so we should do some extra efforts to find the equations. So again, I can send the reference per email, no problem.
Okay, and second question of Bertrand is, how did you detect the presence of Bernoulli numbers in model A?
Yeah. I mean, it's because we have a wonderful collaborator, which is Aline. And, I mean, we can play a bit with this model just using computer algebra. And it's not so complicated to generate terms, in fact. And of course, once you have, I don't know, 10 or 20 terms, which are Bernoulli numbers, I mean, it's a strong sign that we will get this correspondence. But I mean, we also have a proof because we can prove that the series of Bernoulli numbers satisfies the same equation, so we can just match the two things together. But it's a good question. I mean, in these fields, it's often the case that at the beginning we try, we make some computer algebra. So maybe now it will be a ChatGPT, but I mean, for us, it was a Maple. And yeah, we get some connection and then we make some other efforts to prove the connection. Yeah, good point.
And finally, did you need Clauser's results for the D-transcendentality, or does it follow by contradiction from the algebraic closure properties of sum over n, bn, t to the n? Do you see the chat as well?
Yeah, I mean, maybe I should. Yeah, you're right. Yeah. But I think I got the question.
Yeah.
Yeah, no. So I mean, in Clauser's results and also in ours, we do not argue by contradiction. I mean, also in the paper by Clauser, the reasoning is that he was able, I guess, to prove that if there is a kind of differential equation, algebraic one, then in fact the function should be even algebraic. And then it's possible to prove that. So for some reason it cannot be algebraic. So in a way it's reasoning by contradiction. But in ours, it was more direct. I mean, we have this general criterion that we proved in this earlier paper, and we can make it work in general. So yeah.
Okay, Bertrand, is that all right for you?
Yeah, seems so.
Okay. Any other questions for Kilian? All right, this doesn't seem to be the case. So when we thank Kilian again for this. Yeah, please go ahead.
So you mentioned that that the results on the algebraicity or de-algebraicity or transcendence of these functions that it might have application to understanding recurrence of the walks. Is that correct? So could you expand on that a little bit?
Yeah. So the point is that, I mean, I use the word recurrence in two different senses. So, I mean, I'm not sure which one you are referring to. So first, I mean, we can say that a random walk is recurrent or not. So it's a first sense. I mean, if it goes back to the origin or not with probability one.
That's one thing, right? But the other is getting trapped into a certain set of nodes.
Yeah. No, I think, I mean, for this kind of really probabilistic results, I wouldn't say that there is an application of transcendence. I mean, it's, yeah, it would be an overstatement. Um, I think it's quite subtle in a way to have these different forms of transcendence. And really, I mean, the only thing we were able to prove was this a small difference in the green function. I mean, a kind of interpretation of transcendence, but not, I mean, if you take a real, a concrete probability, this, I mean, we are not able to see the connection. So again, you know, I have shown two examples.
So what is the usual, I mean, let's say, not thinking about differential algebra or anything like that. What is the connection? If I simply give you a set of rules, you know, that allow you to walk randomly,
Mhm.
how do you study recurrence? I mean, getting trapped, let's say, in a certain subset of the nodes.
So this I would do by introducing, in fact, the families of probabilities, which by definition are the probabilities starting from a point
Right.
to be trapped at your point. And then we have a discrete, what we call discrete harmonicity relations for this probability, a bit like a harmonic function, not a continuous harmonic function, a discrete harmonic function. And then we try to solve these equations. If you have a finite graph, it will be simple because you are going to have a nice system of equations.
Right.
And if you have an infinite domain, for example, the quarter plane, then you get an infinite set of equations, and it's not clear that you will be able to solve it. But it's how people start in probability. So we just write harmonicity, harmonic equations.
I see.
Mhm.
Is there any way to look at growth rates? I mean, let's say this is an infinite graph. Is there any way to estimate growth rates, let's say in the y direction or in the x direction?
You mean of the number of walks or?
Yeah, the number of nodes or times that is visited or something like that. I know my questions are very vague. Sorry about that.
So yeah, I think the answer is yes. But again, it's more like probabilistic results.
Right.
So I mean, just because maybe it's becoming a bit late, I don't want to bother all of you. The point is that we can connect a random walks, which is a discrete setting, with a continuous setting called the Brownian motion. So it's a very classical, and typically then probability, we use a Brownian motion and we try to
Brownian motion. Okay, Brownian.
yeah, sorry, a Brownian motion. And so we try to approximate a long random walks by Brownian motion. And then we have asymptotic estimates. Of course, it's not so easy, but it's how people at least approach the questions, this type of questions. Yeah.
Thank you. Thank you. Very nice talk. Yeah.
Okay, so we take the opportunity to thank Kilian again for this very nice talk.
Thank you.
And we shall resume next week. Thank you.
Okay, thank you again for the invitation and bye-bye. And if you have any question, just reach me by email. I will be happy to answer.
Okay, thank you.
Merci beaucoup.
De rien, à bientôt.